and welcome to another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 4, Lesson 3, More Work with Dilations. So in the last lesson we talked about what a dilation was. This idea that you could take all the points in the plane, designate one as a center point, then give yourself some kind of a scaling constant, right? And all the other points would then be stretched a distance away from the center or towards the center based on that scaling constant. Now, all the dilations that we played around with in the last lesson, they were all on a one-dimensional number line. Well, we can actually step off the number line a little bit and go into two-dimensional space as long as we've got a ruler, maybe a calculator, and some other tools. So make sure you've got a ruler that measures in centimeters. Make sure you've got your calculator handy, and let's do some dilation work. All right, here we go. Exercise number 1. In the diagram below, we want to dilate segment AB using a center at C and a scaling factor of 2. Letter A asks us to draw ray CA, measure the length of segment CA, and use this to locate A prime, the image of A after the dilation. Use centimeter measurements. All right, let's do letter A together, right? So I'm going to take my centimeter marked ruler, I'm going to put it at my center, and I'm going to measure that distance. Actually, first thing I'm going to do is I'm going to draw in ray CA. Oh, it worked. Okay, now while I've got it up here, I'm going to measure this distance, and that's 3 centimeters. Now what we know about the dilation is that the new A, the A prime, should be 3 times 2, or 6 centimeters away, 6 centimeters away from the center. So that should be right here, which apparently I can't mark unless I do that. So my A prime is going to be right there. Okay. Now, again, what this relies on, of course, is having sort of a number line in the form of a ruler that we can kind of rotate and we can put in any direction that we want. What I'd like you to do now is do the same thing for point B in part B. Why don't you go ahead and do that? All right, let's do it. So we're going to come up here. We're going to put sort of our origin, if you will, at point C. The origin being the 0 point on our ruler. Right? We can see that that's 4 centimeters. So therefore, our new point has to be at the 8 centimeter mark. Whoops, shouldn't mark off 8. I should just mark off B prime. All right, and the other thing that they ask me to do here is to then draw in segment A prime, B prime. So let's do that right now. Okay. And let me move this a little bit out of the way. All right, there we go. So it's not that hard, right? We're doing exactly the same thing that we did in the last lesson. We're figuring out the distance between the center and whatever point we're trying to dilate. Then we use our constant of dilation to stretch, in this case, that point away so that it's now twice as far away, right? A prime is now 6 centimeters away from the center, and B prime is now 8 centimeters away from the center. All right, but now let's get into C, right? Letter C says, measure the lengths of AB and A prime B prime in centimeters. How do their lengths compare? All right, well, this should be easy enough. Why don't you go ahead and do that using your ruler? All right, well, simple enough. Let's go up and take a look really quick, right? If we come over and we measure the length of AB, we find that it's 5 centimeters. And if we measure the length of A prime, B prime, we find that it's 10 centimeters. All right, so 5 centimeters, 10 centimeters, and of course, A prime, B prime is twice AB. And we saw this in the last lesson, right? Even though we dilated point A and point B separately, right, using the same center and the same constant of dilation too, the actual length or the distance between them also scaled by that same constant. So the length of AB started as 5 centimeters, and now the length of A prime B prime is 10 centimeters. But there's also another important thing about these two line segments that we wouldn't have seen in the last lesson, right? So what is it? In letter D, it says, what else seems to be true about segments AB and A prime B prime? Besides the fact, right, that A prime B prime is twice as long as AB, what also seems to be true about those two segments? Pause the video now and write down what you think is true about them. All right, well, hopefully it occurs to you that the two seem to be parallel. And in fact, they are, right? We can say that AB is parallel to A prime B prime. In symbol notation, if you remember this from our work with parallel lines, AB parallel to A prime B prime. All right? An interesting consequence of dilations. Line segments get mapped to other line segments that happen to be parallel to them. It's really a fascinating thing. So let's kind of like summarize and take a look at that, right? When we dilate a line segment using a center that's not on the line segment, and that's really key. In the last lesson, every time we did a dilation, right, it was in this one-dimensional sense, and the center was always on the line segment that we were dilating. But if the center doesn't lie on the line segment that we're dilating, then what happens is that that line segment always gets dilated, has its length dilated by the same constant, right? The new length is k times the old length, and its image is always parallel to the original segment. Literally, what's happening is that this segment is just kind of getting stretched, right? So that it becomes that new length, and yet it always stays parallel to it. You know, regardless of whether that constant is greater than 1, whoops, and now it got a little bit all funky on me, right? Or it's less than 1. Nothing like a demo going awry, all right, in the middle of a lesson. We've all had it happen. All right, so let's keep playing around with these ideas. Let's take a look at exercise number 2. In the diagram shown, segment CD is the image of segment AB after a dilation. Letter A asks us, what is the value of the scaling factor to the nearest hundredth? Always do new length divided by old length. All right, so what I'd like you to do, pause the video now and see if you can figure out what the value of the scaling constant is. All right, well, what's really critical in this case is knowing which one is the image and which one's the original. All right, notice CD is the image. This is the new length, right? This was the old length or the original. All right, and that is so critical because you're either dividing this number by this number or you're dividing this number by this number. And the plain fact is, right, and I'm going to do this again, the way a scaling constant works is we're always taking the old distance times that constant to get the new distance, and therefore the scaling constant is always that new distance divided by the old one. And of course this is where we want our calculators, right? I don't want to have to do 2.7 divided by 4.2 in my head or out longhand or anything like that. We just want to really quickly do it on our calculator. All right, kind of an ugly number, 0.642, etc. We want it to the nearest hundredth, right? And that's 0.64. And if you want to think about this in terms of percent, right, which you could, you know, we could really say that the newer distance or the newer length is 64% of the older one, right? Which means it's smaller than it. Now, letter B is kind of fascinating. Locate the center of dilation and label it point E. Locate the center of dilation. Now, you're going to need a straight edge for this, all right? But given that you need a straight edge, pause the video now and see if you can think about how you can find the center of dilation. Pause the video now. All right, well, for a moment, I'm going to actually go back a screen, right? Remember, if I've got the old one, right, and the center, how do I find these new points? Well, I take the center, I draw a ray through an original point, and then somewhere on that ray, right, is my image point. Same thing over here. If I'm dilating point B, right, I draw a ray from C through B out, and then I locate point B prime somewhere on that ray. Well, we can use that in this problem because we then know, right, we know for certain that the center, and this is going to be probably easier for you than me, the center must lie somewhere on this ray. Somewhere on this ray, right, is the center of dilation. But likewise, the center of dilation must also lie somewhere on this ray. And therefore, the center of dilation has to be right there. Okay? And very often when you deal with dilations of a line segment, right, into another line segment, you kind of get these triangular shapes that are kind of where one triangle is lying inside of another one, right? We see it back in this picture as well, right? We've got this triangle that, if you will, is lying inside of this triangle. Let's keep going. All right, let's take a look at exercise number 3. Triangle EFG is shown below. We want to dilate it using point C as the center and a scale factor of 1/2. All right, letter A asks us to draw rays CE, CF, and CG. Why don't you go ahead, pause the video, and do that now. Draw all 3 of those rays. All right, let me do it real quickly so we've got them up here as well. All right, I'm going to put my center at C. Draw out ray CG, ray CE, and, whoop, of course I had to move it, and ray CF. All right, so I've got those rays in. I'm not going to even move my ruler yet. Letter B. Using your ruler, carefully measure to the nearest 1/10 of a centimeter the distances from C to E, C to F, and C to G. All right. Now, I did not design this problem so that these distances are particularly nice. So do as good of a job as you can measuring those distances and fill them in these blanks. Pause the video now and take a moment. All right, well, let's do it. This is pretty easy now. Let's see, we've got CG, looks like for me, it's about 2.8. All right, CF, that's gonna be the long one. That one, to me, looks like it's about 9.4. And CE looks like that is 3.8. Let me just double check. Yep, looks like 2.8, 9.4. Never hurts to recheck 3.8. All right, great. Now, letter C. Let's take a look. Use your ruler with the help of your calculator to find the locations of the image points so that they are half the distance away from C as the original points. Mark as E prime, F prime, and G prime. All right, great. So by the calculator use, what we're really getting at is the following, right? We know that CE prime must be 1/2 times 2.8, right? And of course, if you don't want to do that division in your head, you just take your calculator out. You can either divide by 2 or multiply by 0.5, whichever you feel more comfortable with, and we find that CE prime must be 1.4. Of course, if you can do these in your head, that's even better, right? Likewise, we know that CF prime will have to be 9.4. 0.5 times 9.4. Let me write that step down, 0.5 times 9.4. So CF prime is going to be 4.7. And finally, let me divide these out a little bit, bring this over here. CG prime will have to be 1/2 times 3.8. And I think I'll just do that one in my head. CG prime will be 1.9. Now, of course, just having all those numbers doesn't quite get us all the way there. And let me see how many things I can block here with my calculator. Maybe move it down to here. Ah, that'll do. Now I actually have to plot the points. All right, so CE prime. Let's do that first. We know that that is going to be, why is that wrong? That's not right. CG is the one that was 2.8. I apologize for that. And CE was my 3.8. Yep. So that would be my 1.9, apologies for this, and my 1.4. All right, let's now do it. So CE prime should be at 1.9. So we're going to put that right here. Move this a little bit out of the way. And there's E prime. Let's now do the long one. Let's find F prime. That's going to be at 4.7. That's right there. Do that. Maybe I'll finish that off and call it F prime. And then finally, CG, right? We should have 1.4. That's right here. Hopefully right here. Come on, no. We'll just go like that. And that's going to be G prime. Whew. All right. Finally. It's kind of hard to dilate an entire triangle. Kind of a pain. All right, so we've located them all. All right. And now, letter D asks us to verify that each side length of the new triangle is 1/2 the length of the original. Well, I haven't even drawn in the new triangle yet. So let's kind of like take a look at what that new triangle looks like. It's kind of cool. All right, let's bring it over here and let's kind of draw it in. Come on. There we go. Right, so we've got this, this, and this. And so you see that smaller triangle, right? Right? G prime, E prime, F prime. G prime, E prime, F prime, right? It's that triangle where every single side has been dilated down to 1/2 the original side. So what we want to do though is we want to verify that, okay? And you want to verify that now, and these lengths should come out pretty nice by measuring the lengths of GE, GF, EF, and then all of those 3 side lengths. So go ahead and do that now, and then let's verify that they're half the lengths. All right, well, let's take a look at them. Right, there they are. So I'm gonna skip all that work, but if you measured them correctly, GE is 4, EF is 6, and FG is 8 centimeters. And then on the nice image triangle, right, let me bring it all the way up. G prime, E prime is 2, E prime, F prime is 3, F prime, G prime is 4, all of which are half of the original lengths. Exactly what we want, right? So, you know, you could see it. You take a picture with your phone camera, right? But you want to make it half the size that it started, right? So there's some center point. You're able to shrink the image by half. Every single length on that image then becomes half as long as it used to be. All right, but you still have to have a center point. There's got to be a center that doesn't move. All right, let's keep working with this. One more problem. Exercise number 4. In the diagram below, we will dilate triangle ABC by a factor of 3 using a center at A. All right, letter A, draw and raise AB and AC. Okay, that's simple enough. Why don't we just do that together? Ah, there's my ruler. I was like, oh, I don't even have a ruler. Okay, so let's draw in ray AC. Maybe I need to make this a little bit longer. Draw in ray AC. And let's draw in ray AB. Maybe bring myself up a little bit here. Okay, great. Now what we want to do is we want to locate points B prime and C prime. Why don't you go ahead and do that on your own? All right, well, it's this simple, right? Point B is currently 2 centimeters away from point A. Therefore, B prime must then be 6 centimeters away from A once dilated. Likewise, point C is 4 centimeters away, and after a dilation by a factor of 3 should now be way out here, 12 centimeters away. All right, so this should be point C prime. Okay, we can now draw in line segment B prime, C prime. I know the problem didn't ask us to do that, but we're going to have to do it eventually. All right. So I'm going to take advantage and do it right now. Now, that's easy enough. Letter D asks us to verify that the length of B prime, C prime, the segment we just drew, is 3 times greater than the length of BC. Well, since we've got the ruler just kind of sitting there, right, I can tell very quickly that this is 9 centimeters long. The question is, how long was BC? And that, not surprisingly, was 3 centimeters long. Showing us, yet again, that even though we dilated point B and point C by a factor of 3, kind of independent of one another, the distance between them, which started as 3, also got scaled up by a factor of 3. All right, now last little piece, letter E. Why doesn't point A move under this mapping? All right, we've talked about this before in the last lesson. Why doesn't point A move? If I dilate this entire triangle, A, B, C, right, using A as a center, point B gets stretched out to here, point C gets stretched out to here, but my contention is point A doesn't move at all. Why is that? Well, it's because it's the center of dilation, right? It's the center of dilation which doesn't move. And again, remember why that is, right? One more time. All right, because we're gonna run into this quite a bit. The whole idea of a dilation is we measure the distance between the point that we're dilating and the center. We then take that distance and we multiply it by whatever the scaling constant is. So can you imagine that? Like you take your ruler out and you measure how far A is away from the center. But A is the center. So the distance A is away from the center is a big fat 0. And then if I take that 0 and I multiply it by the scaling constant, which in this case is 3, I get a big fat 0, which means that A should still lie 0 units away from the center, which means it doesn't go anywhere. All right, let's wrap this up. So today we worked with dilations that weren't just on a single dimension number line. right? We finally did that. And what we saw was we observed something that we saw in the last lesson, which is the length of a segment gets dilated by the same constant that you use to dilate the points. But the other thing that we saw that was kind of neat was that the image line segment ends up being parallel to the original line segment. And we're going to see some ramifications for that as we move forward in this unit. For now, I just want to thank you for joining me for another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.